Today, I want to talk about the end behavior of polynomials. So let's get into it. So if we have the graph of x squared, or a parabola, right? And we want to figure out the end behavior. Well, first of all, what does end behavior refer to? Well, end behavior refers to what the graph does as x approaches positive infinity, and what the graph does as x approaches negative infinity. So now let's think about this. As x goes to positive infinity, the graph will go up and up and up and up, right? So the graph will also approach positive infinity. Then, as x approaches negative infinity, the graph will also go up and up and up and up. So y will also approach positive infinity, right? So now what can we say from this? The end behavior as x approaches positive infinity of this graph is positive infinity. And the end behavior of this graph as x approaches negative infinity is also positive infinity. All right, so now let's erase this and let's look at the graph of x cubed, or something that looks like it. All right, a cubic graph. So here and here, all right? So what happens as x approaches positive infinity? Well, the graph will go up and up and up and up, and y will also approach positive infinity. And what happens as the graph goes to negative infinity? Well, it'll go down and down and down and down, so it'll approach negative infinity. So now from this, we can say the end behavior of this graph as x approaches positive infinity is positive infinity, and the end behavior of this graph as x approaches negative infinity is negative infinity. And we're not going to say, something we're not going to say is as x approaches positive infinity, the graph goes up. Or as x approaches negative infinity, the graph goes down. Well, that is true. That's just not the way we're going to mathematically say it, okay? We're going to say positive infinity or negative infinity. Let's get rid of that, and now we can actually come up with a rule. Let's say we have something in the form ax to the n plus bx to the m plus c, right? Something like this, right? What we want to do is we want to observe this part of the graph right here, and we're going to assume n is the greatest exponent, right? We're going to assume this is in standard form, okay? So what can we say from here? If n is even, right, then a is positive, right? So n is even, a is positive, then the end behavior as x approaches positive and negative infinity will be positive infinity. Then we can also say if n is even and a is negative, right? Think about that'll look something like this, right? Then we can say in both terms, when x approaches positive infinity and negative infinity, the end behavior will be negative infinity, right? Then if n is odd and a is positive, we can say as x approaches positive infinity, the end behavior will be positive infinity, and as x approaches negative infinity, the end behavior will be negative infinity. Then lastly, we can say if n is odd and a is negative, we can say that as x approaches positive infinity, the end behavior will be negative infinity, and as x approaches negative infinity, the end behavior will be positive infinity. Okay, so now let's use that rule to determine the end behavior of a few polynomials. Let's say we have 5x to the 5th plus x squared plus 2, right? Now, what is the end behavior of this polynomial as x approaches positive infinity? Well, let's use that rule. We have an odd power, and we have a positive coefficient, okay? So that means our graph will look something like this. And then in here we'll have some variation, but it will look something like that every single time, right? So from there we can say as x approaches positive infinity, the end behavior will be positive infinity. And as x approaches negative infinity, the end behavior will be negative infinity. Let's get rid of this and let's do another example. Let's do negative 6x to the 4th plus 3x cubed plus 2x squared minus 1. Okay? Now we have something like this. So let's observe. Our power is even, and our coefficient is negative, which means our graph will look something like this. Okay, we'll have some variation up here, but our graph will look something like that every single time, right? So now we can think about what happens as x approaches positive infinity. Well, the end behavior will be negative infinity. And what happens as x approaches negative infinity? The end behavior will be negative infinity, right? So we don't even, once you get good at this, you don't even have to make these drawings. You can just look at our expression and determine what the end behavior will be. Let's do one more example. Let's do negative 100x to the power of 111 plus 30x to the power of 30 plus 1,000. I don't know, right? Once again, we have something like this, and we want to determine the end behavior. Well, this would be really complicated to graph out, right? And it'd be super annoying with these very high powers, right? But all we need to do is look at this term again, right? And we see that this is negative, right? And this is odd. Since this is negative and this is odd, our graph, right, will look something like this, right? And there'll be variation in here, but our graph will look something like that. So once again, we can determine as x approaches negative infinity, our graph, the end behavior will be positive infinity. And as x approaches positive infinity, the end behavior will be negative infinity. So essentially what I'm trying to get across to you is whenever we have an odd power as our largest power, the end behaviors will be opposite. And whenever we have an even power as our largest power, the powers will be the same. And this is something you can use every single time you need to determine end behavior, or even if you just want to determine, did you graph something correctly? If it doesn't follow that rule, you didn't graph it correctly. Thank you for watching. Let me know if I say anything wrong or if you have anything additional to add. Have a great day.